So somebody might be saying for any real computer, the halting problem is decidable using the following argument. So you're given a program and you're given an input and you put it into the following algorithm. You start out by simulating step 1 of the program. So again, you use a simulation here just as in previous units. So you simulate step 1. If the program terminates at that step, then we output yes, and else we record a snapshot of the machine, of the simulated machine, of course. And what I mean by snapshot is something you might remember from the NP completeness proof of SAT. A snapshot is a complete picture of the memory of the machine as well as the line where the program is currently at. And the reason why this algorithm is doing it is it's using one property of an infinite loop, and that is if a machine goes into an infinite loop, then snapshots at some point in time must repeat. So the third step of the algorithm is it takes that snapshot that it has just recorded and compares it against all previous snapshots of the machine. And if it finds just one duplicate, it knows the machine has been exactly at that place before, which means it will also return to that place an infinite number of times. So in that case, the halting algorithm, or at least this algorithm here, which is supposed to solve the halting problem, would output no. And then the algorithm would simulate the next step of the program and go to step number 2. This algorithm would be guaranteed to terminate at a certain point in time, either if the program itself terminates or the simulation of the program indicates that it terminates, or if the program goes into an infinite loop. Here it's important that we have a real computer, because if we have a real computer, we do not have infinite memory. So if we do not have infinite memory and the program goes into an infinite loop, then at a certain point in time, we must have a repeating snapshot. Now, if we had infinite memory, that would not be the case.